Hello guys, thank you for coming to OLED Wave weekly, bi-weekly, monthly paper reading channel. Today we're going to be reading a paper which was published last year. The title is End-to-End Speech Recognition, a Survey. It's by researcher from Google. His name is Dr. Prabhavalkar, Dr. Hori, Dr. Sainath, and Dr. Schlüter, and Professor Watanabe from CMU. Some of them may not just from Google, but okay. The point I want to go over this survey is because more and more people are interested in Whisper model, using that model in their own applications. And besides Whisper, there are tons of open source toolkits which are also claim they're best, but sometimes they do not explicitly mention that what type of structure they're using, and even they're mentioning the structure they're using. People like us want to know whether their architecture has an advantage over the other ones, or what's the limitation of the architectures. If I want to use for my application, which one should I pick? This paper gives a perfect overview of the current existing methods up to 2013. I think it's very, very good. Thank you, Dr. Prabhavalkar. First of all, in the introduction, I think they mentioned classical acoustic modeling is based on a hidden Markov model. Today, I have no time to extend what is hidden Markov model, but just to let you know, I know there are still someone who's working or using the toolkit called CALDI. The acoustic modeling part of CALDI, the acoustic modeling part of the CALDI is still HMM, okay? But they use the DNN, or deep neural networks. But HMM is not mutually exclusive with the deep neural networks. CALDI also use Gaussian mixture models. Okay, this is a very nice reading. The potential of deep learning, on the other hand, initiates a successful approach for integrating formally separate modeling steps. What does the author mean by several modeling steps? Okay, if you look at the CALDI, if you use a CALDI, if you want to launch a speech recognition system, you have to train model, right? But you have to train models. The first model is called acoustic modeling, like we mentioned, it's HMM based. The second model is called language model. So acoustic model does not work by itself. And sometimes you also need to curate or buy or train a phonetic dictionary, or what do you call that? Pronunciation dictionary. So some people call that pronunciation modeling. So that's the third model you have to work with. And so you can see the issue is that when you optimize the models, you optimize them separately, and when you combine them together, so it's not end-to-end or jointly optimized. But they have the advantage. I mean, the traditional hybrid model or a separate modeling step is when you move to a new domain. For example, you go from the general topic to medical transcription, and then you can retrain your acoustic model, but lots of times you just have to fine-tune your language model or adapt your language model to a new domain. Okay, the author tries to generate a definition for end-to-end, especially for speech recognition. Like we just mentioned, joint modeling. Okay, end-to-end does do the joint modeling, and there are several other aspects that he mentioned. You're right. But here he said single pass search. I want to say that end-to-end approach does not exclude a multi-pass search. When you have the output from end-to-end, you can still pass that or plug that into another language model or another model. Joint training, like we mentioned, very important. Training data, training from scratches, secondary knowledge. Okay. Yes, for ASR, when somebody talk about expert system or linguist, these people are usually talking about a pronunciation dictionary, okay, or phoneme sets. Oh, even some people may ask, okay, wait, why people are still using phonemes? Okay, nowadays everybody using word pieces. Okay, like they mentioned about vocabulary modeling in the following section. You can use a byte pair encoding. Everything is tokenized, right? Everything is turned into word pieces, then tokenized. It's simple, right? But let me tell you, for even nowadays, this year is 2024. When people are training their text-to-speech models, so when you want to go from a word level text into sound, they still need a front end to convert the word sequence into phoneme sequence. And they synthesize the phoneme sequence, not the word sequence. Why is that? It's because lots of time, the text-to-speech system, they make pronunciation errors. When they make them errors, because it's an end-to-end system, you have no proper way of control how the word level or word piece level system pronounce. But if the unit is phoneme based, then you have a perfect way of controlling the pronunciation of your output in your speech sequence. Okay, if you pronounce that B as P, it just when you have synthesized the phoneme sequence, you just change the B to P. Okay, generic versus informed modeling. Okay. Okay. Then going from the general definition, he came up with the end-to-end ASR definition. First of all, it's integrated ASR modeling. Second is enables joint training and recognition. Okay. Or the third thing is minimizing the expected word error rate. I know Dr. Prabhavalkar. He is famous for his work on MW, minimum word error rate for end-to-end training. But I would say that even you train the hybrid model, there are still ways of trying to minimize the expected word error rate. But okay, end-to-end is the goal is definitely this, but it's not just end-to-end system has this goal. Okay, avoid separate because nowadays if you talk about this, still Dr. Dampovi, he came up with a toolkit called K2. K2 is you can imagine that it's like acoustic modeling plus language modeling, but allow you to do the end-to-end optimization. In the language modeling, they do use FST, or sometimes they also call themselves K2 FST. Okay. So it also allows you to minimize the word error rate by doing training. Avoid separate obtain knowledge sources. That's something makes sense to me, because in these end-to-end system, usually you do not need an expert or knowledge sources. You just completely rely on data, or mostly rely on the data. Okay, what are my notes? Now I think today I'm just gonna be explain the network structure of the models. I don't think I would have time for the rest, but I would try to explain it later on in videos. But this part you want to read it, but I will skip this. Now they talk about neural network architecture. These are notations, and it's all the problem that these neural network modeling is trying to resolve the probability of the sequence, output sequence given by the input, right? In the training, you want to maximize this. Your output, you want to find the sequence that maximize this probability. Make sense? Here he using sufficient statistics. Suppose you pass X through an encoder, or he called this to be anything called H of X is called high-level representation. Definitely, different people have different opinion on this. I think one professor from GHU, he thought, okay, when you go from X to HX, this is like entropy, right? You just losing lots of information. So HX can be considered as sufficient statistics of X. But definitely, if you look at the neural networks, and if your X is 1 second of audio, you have 16,000 samples of integers, which are 2 bytes per sample, which are 32,000 bytes. But once you pass through a neural network, so every second you would have about 30 frames. Okay. Talking about 30 frames, every frame you're gonna get about at least 124 output. If you're using transformer model, that's about 30K samples, right? And these are in float format, which you have to time 4 bytes per sample. Then you get 120K bytes of information. I should use bits, but bytes is easier for me to say, okay? But in the input, you get about 32K bytes. Then you have more information. What does that mean? Does that mean nobody quite understand, okay? But this is what happens. Okay, go back to the paper. You may ask, okay, wait, why do you say this? This video is mostly for the student who just started their research or interested in their research. I wish my video can help them to ramp up their research. It's not just read the paper line by line. I want to tell you what I think and help you to figure out what you should think. Okay. So the authors, they divided the end-to-end modeling for speech recognition generally into 2 categories. The first is the modeled alignments explicitly through a latent variable. And the second thing is not modeled alignment explicitly. So the keyword is explicitly and probably implicitly, right? And what are the models in the first category? You can see CTC. I just write it down there. Okay, because this is important. RNN-T, RNA. Head is not very common. Okay, and you may see that our CTC and RNN-T are two most common words you probably have listened before. For the other category, they heavily using the attention mechanism So you may heard, okay, AED. Microsoft people like to call this AED. And the Google guys like to call this LAS. And then you may say, okay, wait, where's transformer? Whisper uses transformer model. But I would say that Whisper model is a upgraded version of LAS. How do you say that? In LAS, how do you say this? LAS is not exact transformer model, because if you look at Whisper models, transformer is not exactly the same as LAS. But in concept, they are of the same category. Okay, I will just put transformer here. And you can have a advanced version of LLS. You can say it can use monotonically chunk-wise alignment into the LLS system. Listen, attendance, spell. Okay, so he first started off explicit alignment end-to-end approaches. This is very nice. So I do have a paper reading on CTC. Just Google, just search in my channel. My channel is Ole Wave on YouTube, okay? Search CTC. CTC is a paper published by Alex Grave in 2006. The point of the CTC, also like the Dr. Prabhavalkar mentioned, it makes a very strong independent assumption. This is why the CTC is called a connection temporal classification. C stands for classification. If you're doing speech recognition, you have to recognize or decode a sequence of samples, right? But if you're doing the classification, you only have to give this chunk with this label, so make these independent assumptions, right? This is how they obtain the word classification. And this is architecture of the CTC. Don't forget, this is from time to t. So this is all the samples in your utterance. It's not, so you can ask, wait, is CTC streaming? Let me answer you the question later on. But in this figure 2, this CTC model is not streaming model. What I mean by streaming is that whether the model can output recognition results as you speak, or if it's not streaming, we usually call that offline. Offline means that we have to wait till you finish talking, then we start to work on outputting your speech recognition result. Okay. So once you get pass through the encoder, you have H sub t. Don't forget, H sub t is not just a one frame of embeddings. It's a sequence of embeddings, or you can call that a matrix. Then for each frame or for each row, you get a probability, okay? Probability given the utterance, that the probability of the letter or the word piece is equivalent to a certain character, okay? And then you run the decoding, it's beam search, whatever, greedy search, whatever, okay, you get the output. Practically speaking, this is for people who are just interested in using the CTC model, because CTC model, I would say, compared to all the other papers in this paper, it's weaker or inferior because it made a very strong independence assumption. So lots of time people have to plug in a language model to help it to recognize, okay? For example, here, if you look at some toolkit, which name is, for example, WeNet. WeNet toolkit is very popular in China, okay? According to what I know, it does use a actual language model after the acoustic model or neural network model output. The neural network model can be CTC or CTC plus attention, these type of things. But the unique thing is that they provide very good language model integration support, or how to say that? We call that external language model, okay? External language model. But if you want to use CTC in your product, you definitely want to have a external language model, okay? Then let's move on to RNN-T. RNN-T, the T, it's also by Dr. Alex Graves in 2012 or 13, yeah, 11, 6 years after his CTC. We also have a paper reading, a very long paper reading of RNN-T on my channel. Just to find it, okay? We have a paper reading on this. So I'm not gonna read this paper today because that's gonna take 1 hour, but I will just highlight some key points here and what the author means here, okay? First of all, RNN means recurrent neural network transducer. T means transducer. So it's different from the RNN mentioned by NLP people. RNN-T is also tries to find the alignments during the speech recognition, but it does not make the strong independent assumption as CTC model. You can see in the figure 3, this section or this part is the same, right? And this is the same. What is different is this prediction network. So in the prediction network, the CI means all the output that is not blank. Take this case for example. Suppose you have the output is SE, or what's the next one, right? Is C, right? In RNN-T as CTC, it does output a lot of blank symbols, but blank symbol does not get into input into the CIR. I forgot to draw one thing. So once you output the blank and non-blank symbols, you do the this type of remove blank symbol operation, and then you get the CI, right? That's what it does. So it's a autoregressive method, and it is also time synchronous decoding. Time synchronous is very important for streaming. Time synchronous. Decoding. Anything I talk about time synchronous is about decoding, is not training. But the point is that you can have the streaming now. For some people, streaming is very important. Okay. What does the author mean in this figure? Okay. I don't know why he draw this left to right HMM, but he just want to mention that, okay, this is more like FST. This is all the he want to demonstrate all the possible alignments the RNN-T can have. You can have keep outputting B, but every symbol is ended with but I think there has some issues. Why? In his drawing, you can have SEE, but definitely in the RNN-T, like he analyzed, all the sequence should have length of T plus L. In this case, T equals how many? 7, right? And the L equals 3, or 3 symbols. And there should be 10 symbols in all the alignments. But in his drawing, you can have less than 10 symbols. That is not right. So, okay. In this example, this alignment he drew, what he meant is this. The B here and S, the B here, B here. So you output, every time you output an arc to make you understand easily, right? So you can see for RNN model, it can output a sequence of more symbols in flower C. Okay, does that make sense to you? So at this time point, it will output a, let me use another color plan. Time 0, sorry, time 0. You can output just a B, but at time 1, you output S and B. Time 3, you output this, and then time 5, right? You output 3 symbols. This is why you can output multiple symbols. Then you output just one symbol. All right, Kevin, I think if you have any questions, please raise it now. But if you're not, the meeting would end in 10 minutes. I think I would upload the complete recording onto the channel, and you can watch the rest. Okay. You can just type in the chat. I cannot hear you. All right. So you may see this is a problem. Sometimes you can people saw the problem already on the RNN-T. First, it still make a very strong assumption that the output is only dependent on the non-blank symbols. So let me ask you, what if there are 2 alignments in the past? Let me ask you this: for the alignment like this, S, B, and B, and B, S, and B. So there are 2 alignments. Would that make a difference given the 2 different histories to decode the next symbol in the RNN-T? The answer is no. But in reality, or in people's common sense, I think it matters, because different alignment definitely can generate different results, or should generate different results. This is, but in the RNN-T, you throw away all the blank symbols. So these 2 alignments are literally the same in terms of deciding what the next symbol is in RNN-T. So people make change of it. So they come up with the RNA. A stands for alignment, aligner, or aligner. Yes, aligner. Recurrent neural aligner. But people ask whether they should call RNN-T. No, they don't do that. They just change the name. But I think if you follow the naming protocol of Dr. Alex Grave, you should use RNN-T. And then this part is the same. The only part different is when you have the output A into this, there's no, you can see there's no removing the blank symbol operation. All the alignments are coming in. Definitely this takes more computation in terms of training, but in decoding, it does have advantage over RNN-T. Let's say the author's drawing here, and you can see this time you have a B here, the S here, B here. So what do you see here? I think some of you might have noticed that at each time point, for example, t equals to 0, t equals to 1, t equals to 1, 2, 3, and these are time locations, you only output one and only one symbol. This is significantly reduce the decoder burden or reduce the computational cost, because in the RNN-T model, sometimes it output multiple symbols. Okay, this is the advantage, but definitely let me write it down. But the training is more sophisticated, more complex training. But the decoding is faster, or and potentially more accurate. Why? Because they're using all the alignments, all alignment, all history of alignment, right? Potentially or has the potential to be more accurate or lower error rate. Okay, but because some people have published this, but training RNA is more sophisticated. It takes more time than RNT. Some people would just say, okay, I don't want to train RNA because I can use the same amount of time to train deeper or with model with more data in RNT. I can still achieve better results than RNA. Okay. So let's move on to the implicit alignment of end-to-end approaches. This is AED, acoustic attention encoder and the decoder. Microsoft people call this. Google people call that a listen, attend, and spell. Most other people, they call that transformer. These models are all implicit alignment end-to-end approach. They mostly use it for offline speech processing. Not everybody using streaming speech processing. The key thing here is they use attention mechanism. In this figure, he called it AED, okay, or LAS, same thing. You can see compared to RNT, this part is the same. You still have to wait to the end of the speech. You get, but this time is get a sequence of encodings, and they pass the attention module would iteratively process the input again and again until it outputs a end of utterance or end of speech, end of sentence symbol. Okay, this part is the same. The only difference is the attention and also the decoder. The decoder wise, you can see this output, there's no blank removal part. Why? Because this model, there's no implicit there's no explicit alignment. They just use the output word piece or letters as input of the decoder, and in the decoder they would also send the output the decoder back to the decoder input, and also they got the past status of attention into the decoder. All right. I don't think I want to explain this in the details, but I do have a paper on reading on LAS. I have everything, okay, for you. Just search that, listen, attend, and spell on YouTube, on my channel, okay? I have a detailed paper reading on LAS, listen, attend, and spell. And I do have a detailed paper reading of Whisper. Whisper does not use LAS, but it uses transformer, okay? On my channel. You should read these if you are got interested. But I want to just mention that for the transformer model or Whisper model, I wouldn't say that it's philosophically different than the LLS model, because it also has the encoder and the decoder, and they have the cross attention part, which is very philosophically same or similar as the attention mentioned here. And of course, in the Whisper model, inside the encoder and the decoder, they have self-attention. In the traditional or the original LS, the encoder and decoder are mostly LSTM models. There are no attention. But I can see the difference, okay? There's not much thing, because I think lots of my readers, you guys are very familiar with what do you say that transformer model. This is exactly your knowledge domain. And the point of using this type of AED model or LAS model is that they do not treat the speech signal as a special signal that needs expertise. They just treat the speech sample input as a tokenized, not tokenized, untokenized input, or a sequence of input like the NLP, okay? All they have to do is the pass-through encoder, get embeddings, and the rest is the same as NLP process, just a tokenization, right? Okay, people ask, what if I still want a streaming and I want to use the Whisper model? Then you have to train a streaming version of Whisper. As far as I know, Whisper just released its third version, but it's still not streaming. Whisper is not streaming, okay? Not streaming. But if you're talking about you want to retrain it, it's not impossible. Here I want to mention what we do. Lately, we just roll out a 1,000 hours to 1 million hours of a speech data set with high quality transcription. So you can train your own Whisper model. And you may say, wait, wouldn't that take too many GPU cards to finish this? I would say that it takes way less amount of GPU cards than you want to train a large language model, because speech model usually the number of parameters is on the level of billion parameters, but large language model, they are on the level of thousands of billion parameters, right? At least like at least the 3 magnitudes smaller than the large language model. So, in terms of streaming, you just have to have a local attention encoder, local encoder, which only attends to the current time versus plus a context window. And then you output something, right? Then you shift your encoder rightward, right? You get another frame, then you do this type of thing, together with a history of embeddings. And you can see you didn't see the whole picture. You only get a local window. So your performance, I mean, the speech recognition accuracy would be impacted but you get streaming, okay? I'm not very familiar with this neurotransducer. It seems that it's by the author's colleague. He mentioned the neurotransducer here, but not a lot of people using this. And also, I think lots of people using this concept is called monotonic chunk-wise attention. It says it takes the feature of speech recognition into consideration, because in speech recognition, if you look at attention of these AED models, it's how do you say, diagonal, or it does not need to attend the future. Lots of very few amount of weights is activated regarding the future speech samples. So they can limit the attention. So they call the monotonic, means that the attention is monotonic, and the chunk-wise attention is process the speech audio chunk by chunk. I think WeNet implemented that. This is why I think WeNet is very good toolkit. And also, I believe NVIDIA's NeMo toolkit has also implemented this. Have they? I haven't checked that closely. Okay. But I think NeMo, it more like to promote two things. First is a streaming. They have their CTC plus or RNN-T or RA model. The second, they have the AED model. They probably do not have the Markov implemented. Okay, today I'm just gonna be stopping here to just mention we are a data service company. We offer curated data sets, especially speech data sets, for people who want to train their speech foundation models, fine-tune the speech foundation models, or train their multimodal models. We can provide very large-scale data sets in different languages, different topics, and even different accents and different dialects. And all the transcriptions are high quality and validated. Feel free to contact us. Our email is info@olewave.com. And it is really nice seeing you again. Please don't forget to hit subscribe our channel and keep posted.